So I guess last time we talked about Gaussian discriminative analysis. I'll have a very brief review and talk about some of the remaining points that I didn't get time to mention last time. And then I'm going to move on to another case about span filtering where we're going to have discrete x instead of continuous x. So last time we talked about Gaussian discriminative analysis, and the general idea is that you first model P of x given y and P of y. And what we do is that we say P of x given y is a Gaussian for y is 1 or y is 0. Okay, I guess I need to remember write bigger. So x given y is equals to 0 is from some Gaussian distribution with mu 0 and covariance sigma. And x given y is 1 is from some Gaussian distribution mu 1 and sigma. And recall that we have this illustrative situations where you have some examples like this. These are positive examples, there are some negative examples, and you kind of believe that each of this subpopulation come from a Gaussian distribution with different means but with the same covariance. So that's the methodology we have. That's the starting point we have last time. And then what we do is that we say after you have this probabilistic model, also we have this P of y is 1 is equals to phi. After you have the probabilistic model, then you can learn the probabilistic model from data by MLE. So we learn by maximize. We take the argmax over our parameters, phi, mu 0, mu 1, and sigma, and we take the argmax of the log likelihood. You know, it's the same as the likelihood. You know, argmax of the log likelihood is the same as the max of the likelihood. So I'm just writing the log likelihood, which is the log of the probability of xi given yi plus the sum of the log of the probability y under, I guess, you know, technically under this parameter. Phi, mu 1, mu 2, sigma, and I guess technically I don't have to write phi here just because it doesn't depend on phi. Okay, so that's the methodology, and then we skipped a lot of steps because these are homework questions, and I told you that the solution of this MLE problem, you can analytically solve it in this case because this objective function is nice enough. It's kind of like a quadratic function. So you can solve the maximization problem analytically, and you get some formula for these quantities, right? So the formula for phi was something like something of this form. Of this indicator function, which is here, basically the numerator here is the number of positive examples and divided by the total number of examples. And we also have formulas for mu 1 and mu 2. So mu 1 was something like the average of xi in the positive group, in the positive examples. So you take the average, you divide by the total number of positive examples. And you can also have mu 0 and also sigma. So each of these has a formula, which is a formula that depends on the data. So this is how you learn the parameters from the data. And then we talk about, given these parameters, how do you do the test? How do you do the inference, or how do you do the prediction, right? Like when you already learn these parameters, now you are given an example x, how do you predict y using the parameters and given the x? Right, so, and we said that you are trying to compute the argmax over the two choice of y's, and you want to look at which choice of y give you the largest probability given x, and given the parameter. And these parameters are the solutions you have computed from these formulas, right? So you compute which one, oh sorry, my bad, this is y. You compute which one has the largest probability. And also we discussed that, you know, to know this, actually you just have to, in some sense you have a decision boundary. So the decision boundary between the two choices is those cases where is this those axes where these two probabilities are exactly the same. So where the P of y is 1 given x is equals to P of y is 0 given x is equals to a half. Right, this is the decision boundary. And we have computed the decision boundary, which turns out to be something like a linear function. So decision boundary turns out that this P of y is equal to 1 given x. This is equals to something like I guess maybe I'll just directly write out the decision boundary. We found out that the decision boundary is the set of x such that theta transpose x plus theta 0 is equals to 0, where theta and theta 0 are functions of the parameters that you have learned. There are some specific formulas to describe this theta and theta 0, which are the homework questions. But theta and theta 0 are some functions of phi, mu 0, mu 1, and sigma. So that's why when you really make the prediction, what you do is you find out this decision boundary. This is the family of x, such that theta transpose x plus theta 0 is equals to 0. And then if this quantity is bigger than 0, then you'd say it's positive. And if this quantity is less than 0, you say it's negative. This is a very quick 5 minutes review of the last lecture. Very, very quick. Any questions?
What would be the decision boundary, or actually would there be a decision boundary if we have multiple labels?
Yeah, there will be a decision boundary for multiple labels. So you basically just compute the decision boundary using this methodology. You're going to get a...
So one versus all system, that's what you said?
Can I say that?
Like a one versus all kind of decision boundary? Or what would be the decision boundary?
For multiple labels?
Yeah.
I think if you have the same covariance, the decision boundary is still linear. But if you have different models, you may have different type of decision boundaries.
So will it still be equal to half if we use the same thing?
It wouldn't be a half because you're going to have multiple choices y's here, right? So your decision boundary will be I think it's going to be more complicated. So you have to really decide, when, suppose this is like 0, 1, 2, 3, or 4, right? So then you really have to just really literally solve this, right? You have to know when is the case, what is the region such that the maximizer of this is equals to, say, label 2. So that's going to be something that describes by some linear region, some kind of linear boundaries. But it's going to be more complicated. Yeah, that's a great question. Any question?
Can the boundary be quadratic?
It could be, depending on what probabilistic model you define, right? So I think if sigma are all the same, the capital sigma are all the same, I think it's going to be linear. And if you have different sigma, even you have two classes, but just sigma 1 and sigma 2, then I know it's as a fact it's quadratic. I saw some other questions as well. Any questions are welcome. Okay, so this is just give you a quick overview, a quick review of what we did last time. And you will see that when we discuss the new problem, we are going to have similar methodology. You define a probabilistic model, you solve the MLE, you get some formula, and then you get some parameters, and then use those parameters to predict what's the most likely y's. Okay, so but before going to that, I'm going to discuss one important thing which many people actually asked in the last lecture, at the end of the last lecture. They are great questions. So the question I'm going to discuss next is that why this is different from what we have seen in the first 2 weeks, right? So at the end of the day, you have a decision boundary which is linear, right? So basically, at least superficially, it sounds like you are using a linear model to decide. You are going to use this linear function to decide whether it's positive or negative, right? You compare this with 0, and if it's positive, if larger than 0, it's positive, otherwise it's negative. And this is the same as the logistic regression that Chris talked about in the first 2 weeks. So why this is different from the the so-called discriminative methods that Chris talked about. So I think here is the way I think about this. So so if you have GDA on the left, and suppose you have like a logistic regression on the right, so first of all, in terms of the assumption, they are different. So for GDA, I guess I wrote the assumption there, so maybe I just wrote here again. So this is Gaussian, and this is also Gaussian, something like this. And you also have Y, which is from Bernoulli. And when you do logistic regression, then you just literally say that P of Y is equals to 1 given X. Your probabilistic model assumes that this has the form 1 over 1 plus e to the minus theta transpose X. And recall that here, when you write this, implicitly we are saying that x0 is 1, right? That's Chris' assumption, like in the first 2 weeks. But suppose you don't have that assumption, you're going to have another. Suppose x doesn't contain x0, then you need to have another theta 0, something like this, right? If you contain the x0, then you are going to have a clean form. But they are the same, right? Because if suppose, let's say for today, let's say x, you drop that convention, so x doesn't contain x0, then you're going to write like this, right? And this exactly matches the form here. So basically, you can see that one thing is that for GDA, you assume this bunch of things, and you found out that it implies that Y given X has this form, right? So recall that, maybe I didn't write this, but like this is equals to 1 over 1 plus e to the minus theta transpose X plus theta 0, right? So let's say, how do I write this? So P of Y is equals to 1 given X. Right, so this is a conclusion that we got from the probabilistic modeling, right? From our mathematical derivation, right? We conclude that Y given X should have this form. And in logistic regression, you just directly assume it. So in GDA, that's a conclusion in some sense, right? And I guess we have stressed this many times. So here you model the joint probability distribution, because if you know X given Y and you know Y, then you also have the density of X comma Y, right? But here you only always have Y given X, but you never have anything about X. You only have the conditional probability. So in some sense, the kind of like the main difference between these two is that on the left-hand side you have more assumptions. So I think this is the key. You have stronger assumptions on the left-hand side than on the right-hand side. And in some sense, the general kind of like a phenomenon or the general principle about how do you model what part of the world do you want to model in your machine learning algorithm, right? So do you want to model both, or you want to model only Y given X, right? So how do you decide how much you want to model the world? So the kind of the pros and cons of the kind of the trade-off is that if you have more assumptions, then typically if this is also correct assumption, if your assumption is correct, then this pretty much implies you have better performance. Of course, this is not a mathematical statement, but I think it's kind of reasonably intuitive, because if you have more assumption, it means that you are using your prior knowledge about the world, right? So here you are using your prior knowledge that X given Y is Gaussian. And if you use that prior knowledge, typically if you use it correctly, then you should have better performance. If I tell you everything, then of course you have better performance. But if I tell you a little bit more, suppose I tell you everything about mu and sigma, then of course your performance is the best, right? If you tell you a little bit more about X, then you should always have a little bit better performance. So, but the problem with this is that, so this is the good thing about more assumptions. But the risk is that you may have wrong assumptions, right? You might have, make wrong or approximate or kind of like not exactly correct assumptions, right? Right, so if you make wrong assumptions, then in most of the cases, probably GDA will be worse off. For example, what if the data are not really Gaussian, right? So what if this doesn't look Gaussian at all? And you still make assumption that they are Gaussian, then you're going to have like a worse performance. So, and another thing I want to stress is that even though superficially you see the form here is the same, right? So theta transpose. So when you make the GDA assumptions, you get this y given x of this form. But suppose you go through this left-hand side and get this, and you numerically compute those theta and theta 0, it wouldn't be the same theta and theta 0 as what you computed from logistic regression. So you're going to get a different set of like a theta and theta 0. So that's why it makes a difference. So this theta and theta 0 from logistic regression is, how do you get it? You just directly fit your linear model using logistic regression. That's how you got theta and theta 0. But if you go from here to here, then you're going to first learn the mu, the sigma, the mu1, mu2, mu0, mu1, sigma, and then you compute theta using mu0, mu1, sigma. So that will result in a different set of theta and theta 0. That's why it does make a difference. And whether it's better or not, I think, as I said, basically depends on whether assumptions are correct or how correct your assumptions are. Probably you never can have like exactly correct assumption, but maybe your assumption, when your assumption is approximately correct, then you should do GDA. If your assumption is just completely wrong, then you probably should do logistic regression. Any questions so far?
On this point only, which we touched towards the end, you said that like we'll have a different theta in both the cases. So how will the thetas be different again? Like, is it because the thetas we are computing in that equation out there, are they like? I guess that's the form it eventually ends up taking after training all the parameters, right? So we're not training all those theta, right?
Right. When you do GDA, you are not training on theta directly. You are training the mu's and sigmas directly and using those formulas, and then you compute theta as a function of mu and sigma. Right. So it's definitely a different process, right? You are not getting the theta and theta 0 in these two cases using the same process, right? So in one process, it's kind of circuitous, right? You first have to compute mu and then say theta. And the other case, you just directly fit this using a numerical algorithm, like a gradient descent.
Right. A follow-up to that, like, is it possible that we can get a different equation for the problem p of y given x? Do we have, let's say, different assumptions?
Yep, definitely. You may have, if you change your assumption, you may have a different equation for p of y given x. And there's actually an interesting point I'm going to mention maybe after I answer. Are there any other questions? Okay, so then there's actually another interesting point I'm going to mention next is that even you change the, actually it's possible you change the assumption, you still have the same formula on the right-hand side. So you can have both. Like if you change the assumption, maybe you still have the same formula, maybe you still have a different formula. So this is a concrete case, which I think what I said is actually even more surprising, right? So you change the assumption on the left-hand side, you still have the same y given x on the right-hand side, at least the same form. So this is an example. So I guess here I'm looking at, I think one-dimensional. So suppose x is one-dimensional. Just it's not very important, like exactly. So suppose you do x given y is 1 is from the so-called Poisson distribution. Poisson distribution? Sorry. And then you do this. I misspelled this this word, sorry. But you do this. So you change, it's no longer Gaussian, it's some other distribution. And I guess x is in, because this is a Poisson distribution, so it has to be integer, something like an integer. And then you still have y is, p of y is 1 is equals to phi. Right, so you change your assumption. And then this actually still implies that p of y given x has this form, 1 plus e to the minus theta transpose x plus theta 0. So still the form looks similar. Of course, if you really numerically compute this, it would be a different theta and theta 0, because theta and theta 0, here I'm just writing them as a generic variable, right? But actually they have meanings, right? Theta is a function of lambda 1 and lambda 0, and theta 0 is also a function of lambda 1 and lambda 0. So the form is still the same, but you could have like numerically, if you use this model instead of the GDA, you're going to get different theta and theta 0. So a linear form doesn't necessarily mean everything, right? It also depends on how you learn this linear function. So actually here we have already 3 ways to learn it, right? We can use this model, we can use the GDA, we can use the logistic regression. They will all give you different theta and theta 0 as a final result. And which one will be better? I think if you compare GDA with this Poisson version of this generative learning algorithm, then I guess the answer would be that probably it depends most on which assumption is more likely to be correct. Of course, there's also some type thing here, because here your thing is like in n. But suppose you have a different model which also deal with like R, like basically I'm saying that when you compare it, okay, forget about this axis in anything. Suppose you don't care about that differences, then which model will work better probably depends on whether your assumption is correct or not, or which assumption is more likely to be correct. And when you compare the generative learning algorithm with the discriminative one, I think it's the same thing, right? So if your generative assumption is likely to be correct, then you should gain something from it. Otherwise, maybe you should just use logistic regression. I think in some sense, like these days, if you look at, and also another thing is that, okay, maybe a little more general discussion is that in some sense your model has 2 sources of like so in some sense they are like, in some sense you have 2 sources of knowledge. The model learns from 2 things in some sense. So one thing is that your assumption, and the other thing is you have data. Right, so the assumptions means like how do I probabilistically model all of these quantities, and data is really just what you see, right? So if you have more data, of course it's good, right? If you have more assumption, if the assumption is correct, then that's good. But on the other hand, suppose for example you have already a lot of data, then you have less need to use prior knowledge, because your data already are very telling, right? So like the data is kind of sufficient for you to kind of like extract whatever information you want. Then you don't really need to use prior knowledge, because if you use prior knowledge, you always have a risk to use it wrongly, right? So basically, in some sense, I think the modern trend is that we're going to talk about neural networks and deep learning. In 2 lectures, the modern trend is that now we're in this setting that we have more and more data for many applications, and then so that's why the modern techniques, like deep learning neural networks, those techniques, use fewer and fewer assumptions about our data. So just because, it's not really worth it, right? So like I have to think about how do I model my images, right? Suppose you apply this to images, right? You have to have a model for X, for your image. Does it really worth the effort to do that? Probably not. Of course it depends on the cases, but if you just want a first cut result, you don't have to model your X. Because modeling your X is very difficult, it's very challenging, and you may make mistakes. So you probably should just directly go for the more kind of like a discriminative analysis type of approach, right? So you just directly model Y given X if X is the image, right? But in some other applications, for example, if you think about medical applications, right, or some of the other applications of machine learning, where you don't have enough data. In those cases, I think still you have to kind of use as much prior knowledge as possible. And actually, many times people even do much more complicated modeling of your X, right? So maybe you can use some other more advanced ways to model your X, because you know how does each coordinate of X, what each coordinate of X means, and you know what's their relationship, and you put all of this prior knowledge into your modeling for X, and then you get finally some Y given X using this machinery, and then you predict. And that's more likely to work. So yeah, I guess and another thing is that if you use more assumptions, then you are specializing to your application. right? That's another reason probably why in the modern time, like people somehow don't do this kind of use this prior knowledge that often, because I guess you probably heard of neural networks, and one of the kind of magic about it is that it works for many, many cases without much customization, right? If you use prior assumptions, you use more assumptions, you have to kind of like use different assumptions for different applications, because for different applications, their data probably have different structures, so you have to do it one by one. And that's actually what people do a lot of times, right? So they look at their domain, their questions, and study the structure. But these days, like as you see, like when people use neural networks, because you have enough data, and you just drop assumptions, and you make a model kind of very general, not specialized at all, and then you just apply it to everything just without thinking much about what the data look like. So yeah, so I guess that's we will talk more about neural networks, but this is a preview or kind of connections to what we're going to talk about next. And another kind of like a big picture is that one of the reasons, as I said, in some sense I was saying that this kind of GDA analysis is not used that often, at least not used as often as before, right? Before you have to use these kind of things, and now you can, at least you have the choice to try something like neural networks, and because you have more data. So but still, I think if you are able to model the X, in many cases you can do better. So, and also in some cases you just don't have Y. So even for example when you have images, right? So sometimes you don't have Y at all. You just only have X. And in those cases you just really have to model X, because that's the only place where you can get information from it. And another possibility, another cases is we're going to talk about languages, right? Like especially like this lecture I'm going to talk about language as well, but later when we're also going to talk about languages, solving language problems with neural networks, and there, you're just getting a kind of like a lot of like text from the internet, right? And there's no labels. There's no way, nobody's tell you like which web page is about which. Right, so you just have like raw text. You don't only have X, and in those cases, you really have to model X. There's no way you can get around this. So still, like modeling X is very important. It's just like, for example, it's less important for certain kind of applications because we have more data. Any questions? Okay, cool. So I guess now I'm going to move on to the next question. So I think the question is the so-called spam classification. So you are trying to understand whether a piece of text is a spam email or not, right? So like you have an email spam filter, and you want to know whether your email is a spam or not. And we're still going to do generative learning algorithm. And we are going to have discrete X. So this is another example how you do this generative learning algorithm. You model X given Y, and you execute this like a pipeline in some sense, and learn something out of it. Okay, so so the first thing, so I'm going to get into a little bit more details. How do we really approach this question? So the first thing you probably have to okay.
Yeah, one quick question, like is GDA and like this spam filtering, are these the only kind of generative learning algorithms, or there are more?
Yeah, there are many, many more. These are just examples. Yeah. Right. So I guess so the first question we have to deal to approach this is that how do you represent a text, right? The texts are symbols, right? Like A, B, C, D, right? So you need to make it numerical at least to make the computer recognize them, right? So in some naive way at least, right? So the first question is how do you change the text to some X? Maybe you call this feature, right? This is a you can call this feature vector or representation or something like that. So you want to change this to X in some dimension D, and then you model X. So the first question is how do you represent text? So there are many ways to represent text. So so the way I'm going to tell you is a very naive way. This is like probably I shouldn't say naive, like, but this is like a very simple way. Like, and these days we are gonna have like a, if you really deal with the text, you are gonna use a more advanced deep learning based approach, which we're gonna cover a little bit in probably 3 or 5 weeks. So, so this way, so here the way that we do it is very simple. So what you do is that, maybe I should have some. So what you do is you say you have you first look at a vocabulary. Suppose you have a vocabulary of maybe 10K words. So, and suppose you say you list all of these words in a sequence based on alphabetical order. I guess if you open up a dictionary, the first letter, the first word is probably always A. I think the second, according to some dictionary, the second word is this word aardvark. I think it's a kind of animal. And the third one is the wolf. I think it's another kind of animal. Something like this. And then you list all the words, and maybe at some point you're going to have the word book. And eventually the last word, I think, in many of the dictionaries is this thing I don't even know how to, I don't even remember how to pronounce it. I think I used to know when the first time I teach this lecture, and then I forgot after a few years. Anyway, so you listed all of this, and then you say that suppose you have a piece of text, right? So maybe say, suppose you have a sentence, or maybe an email. Suppose this email just has one sentence, something like I buy a book. So you want to turn this into a vector, and how do you turn it into a vector? So the way that we do it here is that you turn it into a vector that is of dimension, its x is of dimension d, where let's say d is the size of the vocabulary. D is equals to the number of words. So and this vector that represents this piece of this sentence is going to be a 0, 1 vector. So x is actually, it's really from 0, 1 to the power d. There are only 2 choices. And every entry, so you have so many entries. And what you do is you say, if this word shows up in that sentence, then you have entry 1 in this entry. So the word A shows up in this sentence, then I have 1 here. And the aardvark doesn't show up in that sentence, I have 0. And then at some point you have this corresponding entry book. The book shows up in the sentence, I have 1 here. And maybe somewhere I think there's a word probably I here in the list, and then that one would also have a 1. That word also corresponds to 1. And for all the other entries, all the other words that don't show up in the sentence, you just fill in 0 for the corresponding entries. So, and you call this x your representation or your feature vector for this email, for this sentence. So basically, technically, I'm just going to say that xi is equals to 1 if and only if the ith word occurs in the email. So there are actually many other ways to encode, even before using deep learning techniques. But this is probably one of the simplest ones. And you can see that this representation of the sentence is, in some sense, like a super, I guess, like simplistic. Because, for example, you don't care about the orders of the word, right? Suppose you have another sentence, I a book buy, right? That sentence still has the same representation, just exactly the same. And it doesn't care about the frequency of the word. For example, suppose I have a sentence, I buy a book, and a kind of pencil. Then, of course, the representation will change, but these 2 words A and A here, will be counted. You will still have a vector coordinate 1 here, just because the word A shows up in this sentence, but you don't care about how many times the word A shows up in this sentence. So you don't care about the frequency of the words in the sentence. You just care about whether each word shows up. So and you know, there are many other probably issues with this, like what else? Yeah, I guess probably these two are the most important thing, right? You don't have the order, and you don't care about the frequency. But that's what I'm going to deal with, because this is easy, and you can somewhat kind of like do all of the math with this kind of model. Okay, so now what's the next question? The next question is that we need to build a generative model for x given y, and we need to have a model for y, and then we do MLE, and then we solve the parameter, so on and so forth. So basically, I think I can just erase this, and now I'm going to redefine these three things. Right? So that's what I'm going to do. Okay, so let's take, and how do you proceed? So now, because this x now is a binary vector, it's only taking 0 and 1. So you need a distribution that can generate binary vectors, right? So you cannot use Gaussian here. And the kind of the techniques that we are using here is that so-called naive Bayes. So what does this mean is that this means that you just assume x1 up to xd are, maybe I'll erase this now, are independent conditioned on y. So given y, you just independently draw x1 up to xd. Of course, this is not realistic, right? This is definitely not exact, you know, how realistic it is, I think that's subjective, but at least this is not exactly how people generate emails, right? You are not saying that I'm going to generate a spam filter. I first decide, I'm going to generate a spamming email, and the first thing I decide is I decide y, and then after I decide y, I just generate words randomly, right? That's probably not how people write spam emails, right? So, and also that's not how people write the usual good emails. So, but it turns out that in many cases these kind of assumptions are pretty already pretty good. So in the homework, actually we haven't decided whether we are going to include that homework question, but at least there are cases where you can see these kind of things can be very effective, right? Actually, if you just really use this model, even you make this kind of crazy assumption, and you learn some parameters and use this model to classify spams, I think you're gonna get more than 90% accuracy. Maybe these days, as of like 2012, maybe it's not that effective because all the spammers they are adversarial, right? So they know what your prediction algorithm is. They can change their algorithm to kind of fool you, but at least this is a reasonable one if you go back 10 years ago, for sure. So it's kind of interesting, right? So even you make, obviously kind of not exactly the right assumption, but sometimes you can still, because the assumption probably is somewhat correct, to some extent, you can still get a useful kind of outcome from it. And for our purpose, I think here, I guess, to some extent, I'm not really that, I don't care that much about assumptions. I think it's more like I'm trying to demonstrate the methodology. How do you, I just want to give a new example where you execute this probabilistic model, this flow, this pipeline, right? And show how to solve them.
Have you determined how much of the text you use for one example, like for one?
Right. So the question is how does the length of the text matter, right? So here, so one interesting thing about this is that in this representation, the length of the text doesn't really matter. You can encode any length into a vector of dimension d, which is, you can say this is a good thing or bad thing, but so basically you can encode any length, any sentence or any documents into a single vector. And how do you decide what is the window size? Here I don't think it matters that much. Maybe you just take entire email. Yeah. Oh, of course, if you change I think you should just include the entire email because that's the unit you are working with, right? Like for every email, you are classifying whether it's a spam or not. You are not classifying whether a sentence is a spam or not. So that's why you treat an email as a single example.
X1 through XB are independent conditions on Y. Does that mean that, like, if one X appears, that tells us nothing about whether another X is likely to appear? Or does it mean that all X's are equally likely to appear, like, when Y is 0 versus Y?
I think it's more about the first case. So because I do, certainly not all the words are equally likely to appear, right? So basically I'm assuming that given Y, given you have decided that whether this is a spam email or not, every word, they are independent with each other, but they may have different kind of probability. Okay, so I guess let me proceed. So what does this really mean? Okay, now I'm going to do some math, right? So to kind of expand this and parameterize it. So this really means that you have this P of x1 given xt. Given y, you write this as P of x1 given y times P of xt given y. And now I just need to parameterize each of this probability distribution by some parameter. So, and if you think about this, what is this? This is really just a distribution, a Bernoulli distribution, because xi can only have two choices, 0 or 1. So basically, you just have to describe this probability by two numbers, right? Actually, by one number, right? So basically, what you do is that you parameterize parameters of the model is you have phi, say j. So there's some index which I'm going to explain in a moment. You say this is xj is equals to 1 given y is equals to 1. So basically for y is equal to 1, you're asking what's the probability of xj is 1, right? And you denote that probability as this. And then once you have this, you know the probability of xj is equals to 0 given y is 1 is going to be 1 minus phi j given y is 1. And this thing is just a notation. It's not like it's equally the same if I write j comma 1. I write this subscript because it's a little bit more intuitive, but I just need an index in some sense. Does it make sense? So basically, for every j, I'm going to have a parameter. For every j and 1, I'm going to have a parameter that's called phi, and this parameter is in 0, 1. Right? So and this parameter describes this distribution. And for y is 0, I'm also going to have a parameter. So I'm going to write this as j given y is 0. So this is the parameter for the distribution of xj given y is 0. Yes, it's between 0 and 1. This is between. This is the bracket, the hard bracket. Okay, so basically I'm saying that if with this parameter and this parameter, I can describe all of this. I can write out all of these numbers because I describe all the quantities, right? Because for example, what is P of xj given xj is 0 given y is 0? This is going to be equals to 1 minus phi j y is 0. Okay, So, and then I also need to have like something for this to parameterize the distribution of y. Recall that we called this phi before, right? In the GDA case. And now just for the sake of like distinguishing it from the other phis, I'm going to call it phi y. But this serves as the same role as phi in the GDA case. Any questions? So, and then how do I proceed? I'm going to write the likelihood and maximize the likelihood. Right, so the likelihood is the probability of seeing a data given your parameters, right? So likelihood is a function of the parameters. And this is the probability of the data given the parameters. So what are the parameters? The parameters are phi y is one of the parameters. And also all of these phis, phi j given y is 0 and phi j given y is 1. So basically, I have phi 1 given y is 0 up to phi d given y is 0, and then phi 1 given y is 1 up to phi d y is 1. Right? These are all your parameters. So, and my likelihood, here there are two ways I can expand this. So the first thing is that because by definition, the likelihood is the product of the likelihood of each of the example, because all your examples are independent. This is not the naive Bayes yet. This is the examples are independent. So you can just write this as probability of xi, yi, given all the parameters. And here, if you are careful, then you know, okay, so basically all the parameters I'm going to write. I think in my notes, the notation is this. So, but I think this really just means, this is just a convenience notation that denotes all of the parameters. This is the same as this. Okay, and then so far it's the same as the GDA, and then you can also do the chain rule to make this xi given yi condition on the parameters, given the parameters, and then times p of y I given the parameters. So when I use dot dot dots, I just mean all the parameters. Of course, sometimes you can drop some parameters because they don't matter. And then I'm going to again factorize in the dimension of x. Right now, I'm going to use my like this naive Bayes assumption, right, which is the factorization across the coordinates of x. Right, we call that this is x sub I is the coordinate of x. The superscript I is the ith example. So what I'm going to do is that I'm going to use that assumption for each of the examples. So what I'm going to get is I from 1 to n. I'm going to put this in front just to make it simple, make it easier. And if I'm careful, I only have to write phi y here because the distribution of y only depends on phi y. And then I'm going to factorize this thing across the coordinates. So I'm going to have a product across the coordinates, have d coordinates, and then I have p of x sub j I. This is the jth coordinate of the ith example, given the label for the ith example and all the parameters phi jy. Phi jy just means, I guess maybe I would just, so phi jy, this just means a shorthand for this family of parameters. Doesn't make sense. Maybe I will just, sorry, this is a little bad notation. So phi jy just means a shorthand for this collection of parameters. Okay, so
So in this case, there's only two parameters, right? The j is right here and j right is one.
so you mean here?
Yeah.
Yep, that's right. So, right, if you only look at, yep, this j and this j, yes, you only care about you just care about the j and the fixed j and the y is 0 and y is 1. That's
You said earlier we are not using like fixed vectors for some examples, then how does this dependency come from? So if there is no dependency, how can we multiply these
right. So we have two times that we factorize this probability. So the first time is here. So here I'm using the fact that all the examples are independently sampled. So that's why I say the joint probability is the overall examples is the product of the probabilities of each of the examples. And now for every example, of course I first do the chain rule to get x given y. And then I factorize this one into this product again. And this is the level of the naive Bayes. This is using naive Bayes. Okay, cool. So, and then, so I guess you can expect, what we're going to do. We're going to maximize this. And we know that if you maximize this, it's the same as maximize, suppose let's call this L, right? So maximize L, this is the same as argmax of log L. And log L is going to be a sum of the log of this probability. So log L will be a sum. You turn all of these to sum, and you have the log in front of the terms, right? So you have log P yi given phi y plus, here you have a double sum over I from 1 to n, sum over j from 1 to d, and the log of this. And then you analytically plug in all of this, right? So, for example, for this one, you know what is this, right? This is equals to, what is this? This is equals to phi y if yi is 1. If this is equal to 1 minus phi y if y is equal to 0. Right? So, and for each of this, you can write them as a formula of the data and the parameters. And then you do the maximum likelihood. So the maximum likelihood, I guess I'll also just tell you the solution. So if you look at the gradient of L is 0, right? This is the it's a sufficient, it's a necessary condition for you are being for you to be a maximizer. I guess technically I should write nabla y. And you compute this gradient and you solve this equation. This is a family of equations, and then this solving it gives some formulas for the parameters you are recovering. So the final solution will look like this. Phi y is equals to this is pretty intuitive. This is the fraction of positive examples. Actually, it's the same formula as we have seen for the GDA. And then phi j y is 1. This is the probability to see xj is 1 given y is 1. It turns out that this is also something simple. So you look at, maybe let me write down the formula and then interpret it. So what is this numerator? This is the number of occurrences of ith word, right? It's only 1 when the ith word, the ith example contains the jth word, right? So the jth word, right? This is xji is 1 means that the jth word shows up in the ith example. And you also require that the ith example is positive example. So basically the sum is the total number of occurrences of jth word in positive examples. And this is the number of positive examples. So you can see that even though we have done a lot of calculation and modeling, at the end of the day the formula is pretty intuitive. You are in some sense just counting. It's kind of like something about counting, right? You're doing some statistics, right? You're counting how many times the jth word shows up in positive examples, and you divide that by how many total positive examples there are, right? So for example, suppose the word book shows up in 10 positive examples, and there are like a million positive examples. That means this is 5 over a million, which kind of means that book doesn't seem to have much correlation with positive examples if this number is small, right? If this number is small, it means that it's unlikely to see the jth word given positive example. So when it's unlikely, it's unlikely partly because the data they don't show up. So okay, and for the negative examples it's the same. So you just write it's kind of symmetric. So phi of j given y0 is equals to something like I guess you can guess what it is, right? Basically, you just change the value of y to 0. Any questions? Okay, so so basically we are done with this. At least we are almost done. There's one small thing that we have to address, but in terms of the estimated parameter, we are done. So, and we got the parameter, and at the prediction time, as before, right? So when we do the prediction, as usual, you want to compute p of y is 1 given x, right? And if this number is larger than 0.5, then you say this is a positive example. If this number is less than 0.5, you say this is a negative example. So we have to compute this. And how do we compute this? This is, again, as in our general methodology, you use the base rule and divide by p of x. So this is still the same. But there is one small caveat here, which is that what if you have a 0 divided by 0 situation? So before, when you have Gaussian, the density, no matter what you do, the density is always non-zero at every places. Even though sometimes it could be very small, the density could be very small, but still, px in all of these quantities are all positive, strictly positive. At least you're going to get a ratio here. But here, there might be some cases where your p of x is just literally 0. And why that can happen, I guess maybe let me just give you an example. So you may think that some example just never shows up, just because of some, I guess let me show the example cases, right? So suppose, maybe let's say suppose, so suppose maybe the word aardvark never appears in training set. And I'm claiming that this would mean that if you have but your test example contain it. So let's say test example, let's call it x, contains it. And I'm going to claim that p of x will be considered as 0. Why? I guess let's somewhat simulate this algorithm and see what the phi we're going to compute from this. So advoc is the second word, right? So j is 2. So and you know x2j, x2I is 0 for every I. This is a mathematical translation of advoc never shows up in the training set. For every example, the second word never shows up. That's why the x2I is 0. And when the x2I is 0 and you plug it into this formula that tries to estimate this parameter, suppose let's try to estimate the parameter phi 2y is 1. Right? This parameter intuitively means that how likely the second word will show up in a positive example. And recall that this formula is really about the total number of occurrences that ith word shows up and divided by the total number of positive examples. So this will be 0 because no occurrences of the second word divided by the total number of positive examples. And this will be 0. That's still fine. So far it's not a problem. So 0 divided by a positive number, that's fine. And phi 2y0 is the same. It's 0 over the total number of negative examples. This is also 0. So basically, according to your estimate, MLE estimate, this word advoc just cannot show up at all, right? Which makes sense because it didn't show up. It didn't show up in the training set. You just in your estimate you also say it shouldn't show up at all in this under this set of parameters. So, but that's a problem because now if you compute p of x for example x that does contain the second word, then you're going to write this as p of x. So how to compute this? You use the total law of probability. You say this is equals to the case when y is 1 plus the case when y is 0. And of course, this is a positive number, this is a positive number, that's fine. But this one is equals to, maybe I'll just, this one is equals to using naive base, this is equals to xj given y is 1. And you have some product over j from j to d. Right? And now I know that my x2 is 1 because this word does show up in this email. And that means that p, you're going to have p of x2 equals to 1 given y is 1 as the second term in this product. Right? So you're going to have this term shows up in this product. But this one is equals to phi 2 y is 1, which is equals to 0. So just because of the second word, according to your model, it's not supposed to show up, but it does show up. That means that this example just does have 0 probability in your probabilistic model. So that's why this is 0. And for the same reason, so this one is going to be equals to y0. And also, you have this term p of x2 equals to 1 given y0. And recall that under your probabilistic model you learned, you just think this word cannot show up at all. Right? The chance is 0. So that's why the chance to see this word shows up is 0. So this is 0. So that's why this is also 0. So because these 0 terms, eventually, I guess because there's a 0 here, there's a 0 here, so you get 0 just eventually. So basically you conclude that this example just isn't supposed to show up. Like this example has 0 probability under this probabilistic model that you learn. So, and then that's a problem because now this p of x is a 0. This is 0. So you have something divided by 0. Actually, this is also 0 if you think about it, because this is just the one term the numerator is just one term in the decomposition of px. Right? The numerator is just this term. And px is the sum of the two terms. So both of these, the numerator and the denominator, they are both 0. And you have the 0 divided by 0 situation. And what do you do? So this is an issue. And this is a reasonably realistic issue because sometimes you just see a new word in your test example, right? You haven't seen this word at all in the training set. So the way we deal with this is so-called Laplacian smoothing. In some sense, this is a way to introduce a little bit prior so that you don't 100% trust your training set. So basically what we are seeing here is that you trust your training set just 100%, like religiously in some sense, you haven't seen any word, the word advocate, right, in the training set. You just, and because of that, you trust it, you just say, this word just shouldn't show up at all. That's why if you see this, if this word is in this X, right, so then the probability of X is just 0. So what we are going to do is we're going to say, okay, just maybe we shouldn't trust the data exactly. We are going to allow any new word to show up a little bit with some small chance. And it's in some sense, this is a local adjustment by using some prior knowledge, which is called Laplace smoothing. So I guess the best way to describe this method is start with something abstract. For the moment, let's forget about that for the moment and just think about the abstract question. Suppose you have so a simple example. Maybe you can call this example or abstraction in some sense. So suppose you think about you estimate the bias of a coin. Right, suppose you have a coin, this coin is biased, it's not 50-50. So how do you know the bias of the coin? Or in mathematical language, it really means that you have a random variable z, which is from Bernoulli. Where with a parameter phi, and this phi is something unknown, right? It's not a half, and you want to know what the phi is. And you want to know it by looking at some data, right? So you draw a few copies from this distribution, and you want to know what's phi. You want to estimate phi by using the data. And you want to solve this problem, right? This is still a probabilistic model. You can still do the same thing, where you can write out the probabilistic. You can write out the MLE, and you can write out you can maximize the MLE, right? So let's try to do this. So suppose you have maybe n trials, and let's call this z1, z2, and zn, and each of these is either 1 or 0, something like this, right? Maybe I guess in my notes it's called tail and head, so I'll just call it tail and head, something like this. So and you want to estimate what phi is. And if you follow our general principle, right, we'll try to write out the likelihood. Then the likelihood, what is the likelihood? So the likelihood of phi, right, of the parameter phi, is the chance to see this data set given the parameter phi. So what's the chance to see this data set? The chance to see the first one is 1 minus phi. Right, the chance to see the second one is 1. I guess tail means, I think I need to define tail means what? Tail means 0, let's say. And head means 1. Right, so the chance to, and you have the probability to see 1 is phi, and the probability to see 0 is 1 minus phi. So that's why the probability to see the first example is 1 minus phi, and then you time 1 minus phi for the second example, and you multiply a bunch, and then you multiply phi at the end. Right, this is the likelihood. And if you organize this, right, you count how many 1 minus phi there are, how many phis there are. This will be 1 minus phi to the power of the number of tails, and times phi to the power of has. Actually, if you really look at this example, you will see that the formulas are very, very similar. Actually, this example is a toy case for that in some sense. Okay, so you get this. And then you can take the argmax of this log likelihood. You take the argmax of the log likelihood. So the argmax, maybe let's call this L phi. So the argmax of log of L phi, if you solve it, you're going to get the following. So it's going to be the number of has over the number of has plus the number of tails. Which also makes sense because this is basically empirical frequency of seeing the has. By empirical, I just mean like the frequency of that you see the has in the training set, right? And that's your most likely estimate for phi. Okay, so and right, so okay, so far everything seems to make sense, right? So, but now let's consider a somewhat kind of extreme case. So what if you see all the examples you see are tails, right? And you don't have a lot of suppose you just have 3 jaws, Z1, Z2, and Z3, and they are all tail. So according to this formula, you're going to get the phi, the best estimate for phi is 0 over 0 plus 3, which is equals to 0. But should you really trust this, right? Should you really trust that this coin just never give you a head, right? What does this mean? This means that this coin just never give you a head at all, forever, right? Should you really trust that? This is a little bit subjective, right? You may, if you are really trusting the data, you can say yes. But maybe you have some prior knowledge that most of the coins are not that crazy, right? So probably you should at least have some chance to see the head, right? With some chance. So in some sense you can say. So basically, on the flip side, you can say, okay, maybe this is just some coincidence, right? It just happens that you see 3 tails. Even this phi is a half, right? Seeing this example, seeing this cases is the probability to see this case is at least 1 over 8, right? It's something like 1 over 8. So maybe it's just coincidence of the data set. So maybe you shouldn't trust the data set that much. So the so-called Laplace smoothing is a way to, in some sense, incorporate a prior so that you say that my coin shouldn't be extreme, shouldn't be too extreme like this. So basically, if the Laplace smoothing refers to the following estimator. So if you use the Laplace smoothing, you're going to have a different formula. Your phi will be equals to the number of has plus 1 over the number of has plus the number of tails plus 2. So this formula, I didn't tell you any a mathematical justification. Actually, if you really look into the literature, there are mathematical justifications. So far, I'm just telling you the formula. But it would solve this problem, right? At least to some extent, because for this particular case, you are going to get 1 on the numerator and 4 for the denominator. So instead of getting 0, you are getting 1 over 4. So still you say, okay, the chance to see the head is pretty small, right? It's smaller than the chance to see the tail. But you don't have a very extreme estimate. So, and you can see that this Laplace smoothing is mostly useful when you have not enough data, right? If you have a lot of data, then this Laplace smoothing is not doing much, right? Maybe let me give you kind of a example. For example, suppose you have a big data where the number of has, let's say, I guess I'm making up this, right? So 100, and number of tails is 60. So if you use the standard approach, right? If you use the standard approach, or maybe I shouldn't call it, the vanilla approach, then this is the phi would be equals to 60 over 60 plus 100. Right, this is, what is this? This is I don't know what it is, this is something like this. And then if you use the Laplace smoothing, then this phi will be 60 plus 1 over 60 plus 100 plus 2, which will be 61 over 162. This is 60 over 160. And these two are just very similar. Just because the 1, whatever you change here, 1 and 2, right? It doesn't really matter that much because the dominating term is the 60 and 100. So sometimes you achieve you achieve a kind of right balance, right? If you have enough data, then your prior or like your Laplace smoothing is not doing much. It doesn't really change much. You trust your data. And if you don't have enough data, then Laplace smoothing would try to make it not too extreme. Would try to make your estimate not too extreme. Okay. So now let's go back to our problem. So let me see where is the best way to write this. Oh, I think I erased the. Oh, I erased the formula, but I'll write it again. Yeah. So going back to our spam filtering thing, I guess actually there's one thing that is left here. This is our estimate, right? And our other estimate was something like phi j y is 1 is equals to am I writing the superscript correct? I think this is I, not bad. Right, so if you apply this to our case, so you can recall that in this case it's kind of like you are saying that the numerator is the number of times this word shows up in the positive example, and the denominator is like the total number of positive examples, right? So in some sense, the analogy is that this denominator is very similar to the number of heads and tails, because the heads means that this word shows up, the tail means this word doesn't show up. So and here the denominator is like the total number of times, total number of examples, positive examples. And here the numerator is the kind of like the heads, right? So basically heads means that the words show up in a positive example, and tail means that the word doesn't show up in a positive example. So that's why this is like a heads, number of heads, and this is like number of heads and plus number of tails. And if you use a Laplace smoothing, then you are going to add 1 to the denominator, and you add to the numerator, and you add 2 to the denominator. So that's the Laplace smoothing. And the same thing for the other formula. So you're going to add 1 and add 2 here. So that's the Laplace smoothing. And why this solves our problem? It solves our problem because now we just never estimate any parameter phi to be exactly 0, right? So recall that when we have this advac issue, right? So the issue was that these 2 parameters for the advac was exactly 0. Yeah, let me ask.
Should we do the same working while though as the in frequent or one of the classes that we come up with, just when the same concern?
Yeah, that's a fantastic question. So the question was that whether you want to do the same Laplace smoothing for the phi y, right? Phi y was the single scalar to describe the probability of y, to describe the probability of each of the class, right? So, and you are right. So suppose one class just never shows up, right? And you only have like negative class or positive class, then you probably should use Laplace smoothing for that. But I think this is a little bit less important because in most of the data set you have to see positive examples and negative examples. You have to see a reasonable number of them, maybe 50 of positive, 50 of negative. And then Laplace smoothing wouldn't really matter that much. You can still use it, but it wouldn't matter that much. Okay, so going back to this, so recall that our problem was that when you have when you estimate parameters, you get this 0, right? You thought that artifacts shouldn't show up at all, right? You get this very extreme estimate. And now, when you add this 1 and 2 here, what you're going to happen is that instead of having 0 over the number of positive examples, you get 0 plus 1 over this plus 2. Yeah, I don't have a different color, sorry, so I have to just modify. I just only have black pens. So you get this. And then this will be at least no longer. So this will be still a pretty small number, right? This is 1 over the number of positive example plus 2. So but at least this is bigger than 0. So, and the same thing for this, right? So you're going to get plus 1 over, and this plus 2, and this is bigger than 0. So if both of these are bigger than 0, then when you evaluate this formula, you are not going to evaluate to 0. So your p of x will be some positive number. So then you can get a number of the p of y given x. And maybe just a very small extension, given we have 2 minutes, so 2 or 3 minutes. So if you have more than 2 classes, you can, this is just for your interest. So suppose you have like maybe a dice, something like that, right, instead of like a coin. So suppose you have z, which is from something like 0, 1, up to k minus 1. So you have k choices. Then the general Laplace smoothing would be something like, if you don't do Laplace smoothing, what you're going to have is that the chance you estimate this to be something like the number of times zi is equals to j over the total number of examples. So you count how many examples kind of end up to the choice j, and you divide by the total number of examples. And if you use Laplace smoothing, you're going to add 1 to the top, and you add k to the bottom, where k is the number of choices. So this is just a small extension of Laplace smoothing. I don't think this course will use it again, but just for your interest. Okay, cool. I guess that's pretty much all for today. Any questions? Okay, great. Yeah, in the next lecture, I guess we're going to talk about kernel method, and then we're going to talk about deep learning. Thanks.